Alright, scholars, we are going to take some quick notes on the horizontal range equation, which you can see looks kind of like a disaster. We're going to show you where that comes from here, and it's just going to come from these two sets of equations, our x and y equations, and we're going to draw a picture, set it up like we normally do, and so on. Before we do that, I just want to show you what we're talking about. So what we're going to be specifically talking about here, I've got the projectile motion lab that you all played with a little bit. So you can do very generic style projectile motion problems. And so for example here I can move the cannon to whatever angle I want, let's say 52 degrees and some initial speed of 27 meters per second. That's going to go off the screen. 20 meters per second. So you do that, you launch it, and you can make a prediction. Let's take the speed down a little bit. You can make a prediction. And what we want to be able to do in physics is be able to predict, for example, where this would land. So we don't want to just measure it after the fact. We want to be able to predict where it's going to land. Now, for various reasons, which we will discuss, it's going to be much easier to do a very specific type of projectile launch. So what we want to do is we want to restrict our launch to be launched specifically from the ground. So you can see this one here says it's going to be launched from a height of 0 meters, and it's going to land at the same location. It's going to have no y displacement. And what we want to be able to do again is to predict where it's going to land here. It was about 17 meters. With that, we will come back over to our notes, and we're going to try to show how you can derive this equation, which we have up at the top, which is a super useful equation, and then we'll actually solve a problem related to that, and we'll check it on the simulation. So we're going to do what we normally do, and we're going to draw a picture. It's really important here that our object is launched with some initial velocity and some initial angle. It needs to launch and land at the same height. Okay, very, very important that it does that. So we want to develop this formula, and what's kind of cool about this formula is you notice that it only has two variables. It only has the initial velocity and the angle. So we want to predict where it will land using only v0 and the angle theta. Okay? Which seems like you wouldn't be able to do that, but you actually, in fact, can. We're going to do this in a clever way. So, again, what we're trying to find here is what is the x position, delta x. What is the final displacement in the x direction? Let me clean that up. And then the other trick that we're pulling here is that the y displacement, the overall y displacement, is going to end up being 0 in this case. What I mean is, of course, the object launches here and lands here. So I'm going to label that in red. The final change in y position, the y displacement, is 0 because it starts and ends at the same location. A couple other facts that we'll just include. It's possible that they will be useful. I want to remind you, though, at the top of this thing's arc, I didn't draw it very symmetrically here, but at the top here, at the maximum height, so at h max we could call it, we're going to say that the y velocity, we'll just say the y velocity there equals 0 meters per second. So in other words, at the top, it keeps moving sideways, but it stops moving upwards or downwards just momentarily. So again, we are after the x displacement, and that's what we're going to try to solve for. So in order to set this up, we're going to use our equations here. And what we need to do before we do anything else is set up our trig information. So let's do that right over here. I'm going to break out this little triangle, and we'll set it up in a more coherent way. I'll blow it up just a little bit so you can see it. So there is our initial velocity vector. It is launched, of course, at some angle that we're going to call the Greek letter theta. And that means we have an initial velocity in the y direction and an initial velocity in the x direction. And what we want to do is, using trigonometry, we want to set that up. So I'm just going to blindly write down sine theta, cos theta, and tan theta. We don't know which of those is going to be useful to us yet, but we know that we're going to need that information in some way. Now, Sine theta is equal to the opposite side over the hypotenuse. So the opposite side over the hypotenuse would be v naught y over v naught. Okay? And cos theta would be adjacent over hypotenuse. That's v naught x over v naught. And then I'll just scratch that out and move it down. So tan theta, if we're going to end up needing it, is opposite over adjacent. So v naught x over, v naught y over v naught x. Opposite over adjacent. Okay. Because we're going to need it here in just a moment, you'll notice that in this equation we need v naught x, and in these equations we need v naught y. Let's solve these since they involve those two terms. If I multiply both sides by v naught, I end up with v naught sine theta equals v naught y. That's really nice. We're going to need that information. We also need the v naught x information. That's as sloppy as I wrote it. That's what this is. So if we multiply again both sides by v naught, we get v naught cos theta that equals v naught x. So what we have is a way to calculate the initial velocities up and sideways as our projectile is launched. Okay, so the next thing that we're going to do is we're going to take our x equation, and I'm just going to tell you, we're going to use this first y equation. The main reason for that is that we can plug in the y displacement is 0 right there. And it's going to make things much more simple. So check this out. We're going to take the first equation, which is the x displacement. So the x displacement is v naught in the x direction times t. And lo and behold, we have v naught x right here. So we're going to plug this in right there. And we'll rewrite this the x displacement, which is, again, remember that's what we're looking for, the horizontal range. And we're going to plug that information in. So v naught cos, just multiplied by t. So if we know the initial velocity, which you could see there in the simulator, we can get pretty easily. If we knew the angle, which again is very easy to measure both in the simulator and in real life, and knew the time, we'd be able to easily calculate this. Now I'll just tell you we don't have enough information yet. So what we'll do is we'll pull down our y equation. The y displacement is v naught y t minus 1/2 gt squared. And then we're going to plug in that crucial fact, because we launch and land at the same height. The y displacement is 0. So I'm going to do two things at once here. I'm going to write 0 here. That's the y displacement. And I'm going to substitute in what v naught y is right here. So that's going to be v naught sine theta times t minus 1/2 gt squared. And then I'm going to try to solve this for t, because remember, all we need to solve for x, like to get the x displacement, these are easy to measure. I need to know the time. We're going to get it from over here. So in order to do that, take a second, see if you can solve this for t. All right, so what you need to do is get the t's on opposite sides so that we can solve. So let's add 1/2 gt squared to both sides. Adding this to both sides. That equals v naught sine theta, all in parentheses, times t. Then I need to cancel a t on both sides. All right, and I'm left with t 1/2 g is v naught sine theta. Now I just need to divide by g and multiply both sides by 2 to get t alone. So I need to multiply by 2 and divide by g. So we cancel, and we're left with t equals 2v naught sine theta all over g. Okay. So what does this time represent? Well, this time represents the amount of time, if we launch something with this initial velocity and this angle, for it to go this distance. We would call this the hang time. Okay? And what we're going to do is we're going to plug that in right here. And it's going to look like a mess for a moment, and then we're going to clean it up. So check this out. we're going to plug that information in here. I'm going to switch colors so that you can see we're on the sort of last step here. So the x displacement is this information, v naught cos theta, that doesn't change, times t, which is our hang time equation. So I'm just going to plug that straight in there. 2 v naught sine theta all over g. That looks terrible. Let's clean it up just a little bit. You can see I have a v naught and a v naught, and let's pull the 2 out front. So actually I'm going to write it in a very specific way. X equals v naught squared 2 sine theta cos theta all over g. Now if you are in pre-calculus, you may recognize this trig identity, but basically, and I ran out of room, so I'm going to write it over here. This is a trig identity. We're just going to call it a trig ident for right now. This is a fact that you do not need to know for physics, but this is a fact we're pulling from pre-calculus and calculus. Basically, anywhere where we see this, 2 sine theta cos theta, you can just simply replace that with what's called the double angle identity. So instead of it being 2 and a sine theta and a cos theta, you just have sine times 2 theta. Now, I have a video posted if you really want to know why this works. I think you should want to know. But if you want to know, you can see why that works. Anyway, the moral of the story is anywhere where we see 2 sine theta cos theta, we just straight up replace it with this. So check this out. This is the actual last step. So the the x displacement, so where will the ball land, is the following. V naught squared, pardon me. Then we'll do our substitution. Sine 2 theta all over g, and that is it. So the first thing we want to do is let's take this for a spin. Let's actually just come up with 2 numbers to plug in for v naught and theta. And let's make a prediction on paper, and then let's check it out in the simulation. So I'm going to just move on to a new page. So I'll recopy it here. So the x displacement, v naught squared sine 2 theta all over g. What did I have in there? Let's pick 15 meters per second, and let's do 30 degrees just for fun. So I'm not going to click the fire button. We'll just replace this here. So we don't know where it's going to land. We'll write this information over on our paper, and let's see if we can do the calculation. So there's our equation. We said that v naught is going to be 15 meters per second. Our angle theta is going to be 30 degrees. Now again, if you are a savvy pre-calculus person, you might notice that 30 degrees is a nice angle when it comes to using trig. We will often use nice angles. So let's plug that in. Let's get out our calculadoras and do the calculation. So the x displacement is going to be v naught squared, so 15 squared, sine of 2 times 30 degrees, all over 9.8 meters per second squared. Now, of course, I included my angle for my units. Let's make it meters per second inside of there. Okay, that looks good. Let me show you what this is going to look like plugged into our calculator. So we're going to have 15 squared times, hold on, pitfall here. Let's make sure that we are in, I was in radians. So you need to make sure you click the mode button if you have a graphing calculator like this, and go down to where it says degrees. We're going to be doing this in degrees, and you can say second quit. Okay, so 15 squared times sine of 2 times 30, that's just 60. You can also type 2 times 30 in there, that's fine. We're going to divide all of that by 9.8. We already accounted for the negative. And we get 19.88 meters per second. And by meters per second, of course, I mean meters. So the x displacement is going to be, again, what did I have? We'll round that to 19.9 meters. And so that's our prediction. What we're saying is that if you launch something at an angle of 30 degrees, it's going to have an x displacement of 19.9 meters. We made that prediction. Let's go check it out in the lab. I'm going to move this to 19.9 meters. We're going to hit the fire button. Fingers crossed. So we're going to launch it and see what happens. Boom, it hit right on 19.9 meters. Science works, physics works. Awesome. You'll notice that I actually had air resistance turned on there. And the reason that that appears to have worked and given us the result we expected was because I used a cannonball. Let's see what happens if I use a... Oh, these are some weird ones. Let's see what happens if I used a baseball instead. You'll notice the baseball is much lighter. Let's launch and see what happens if we do that with a baseball. Check it out. Oh, wow. So the baseball was considerably shorter. So with air resistance, the baseball went about a meter shorter. Now, to be clear, that's not a general rule. If we throw something else in, for example, let's say a tank shell. No, let's say a car. Okay. What happens with the car? Wow. Car went exactly where we expected, 19.9 meters. So it depends on the air resistance where it will in fact land. So we predicted 19.9 meters with a cannonball. Even with a little bit of air resistance, we got the correct answer. What we want to say is that this assumes air resistance is negligible. Hope I spelled that right. That means that we can ignore it. And this also assumes we are near Earth's surface. That makes G a constant. G will change if you go too far away from the surface. The final thing that we assumed here, which is critically important, is that delta y is 0. If you have a situation where this is not true, so for example, if you launched off the top of a cliff and landed way down here, this equation would certainly not work. Anyway, folks, you're going to have a bunch of questions just like this one, and you're going to be playing around in the simulation. Thank you so much. Good luck out there, scholars.